Okay, new unit, yay! So we're going to do quadratic functions this unit. It comes off of the factoring that we did. We're going to take a more visual perspective to when we factor what it's going to look like graphically. And so let's go ahead and start with just talking about what quadratic functions are, what they look like, some basic parts of the equation for today, and then we'll kind of develop those skills as we continue in this unit. Okay? All right, let me zoom out a little bit here. Okay, so introduction to quadratic functions. So do you remember how we wanted you to memorize the equation for a line? Okay, so the equation of a line is y equals mx plus b, right? We have just an x with no exponents, nothing going on that's too crazy, and something keeps getting added. All right, that's it. For exponential functions, we memorized the equation y equals a times b to the x. And either this could represent a doubling growth, a tripling, halving, and putting those numbers in here, or if it's a percent, we had to change it to a decimal and either add it to 1 or subtract it from 1. Okay, so you remember those, right? So now our final equation that we need to memorize is for quadratic functions. Okay, so linear functions look something like this. Exponential functions look something like this. This would be a growth one. And now we're in quadratics. And with quadratic functions, I want you to memorize y equals ax squared plus bx plus c. Now, you'll never have to write it with the a, b, and c, but we do need to talk about what the pieces mean. So in memorizing this, it's just going to help you when you go to factor it, because we're going to rewrite these in different ways. Sort of like how for the equation of a line, we also had the equation y equals m times x minus h plus k, right? And how those could be put back and forth. Like if you wrote it this way and distributed and combined, we turned it into that. It's kind of what we're going to do here is we're going to learn different ways of writing this quadratic function. So this is the one we're going to talk about today. This is called standard form. Okay, right? Highest power to lowest. And then talk about what the A, B, and C mean for this graph, specifically the A and the C. Okay, so in this quadratic equation, I want you to notice what it looks like. Okay, the highest exponent will be a squared. There will be no x to the thirds, no x to the fourths, no square roots, nothing weird. It's literally an x squared, and then it could or could not have other pieces with it. So it could be like y equals 3x squared. It could be y equals 3x squared plus an x. And it could be y equals 3x squared plus an x plus a 4. Okay? But it can't be anything that doesn't have a squared, or else it would be a line or an exponential function or something different. So it has to have a squared, and it can have other numbers as well, but it has to be of lower power. You can't have cubed, you can't have fourths. So we'll talk about that here in a minute as well. So in the quadratic equation, why is it important for the leading coefficient to be non-zero? What does it mean to be 0? If I made that leading coefficient, so let's remember what a leading coefficient is, right? In y equals ax squared plus bx plus c, that a, b, and c would be technically real numbers, right? The a value is your leading coefficient because a coefficient is any number in front of a variable, means how many variables you have, and the leading coefficient is the one that's in front once it's written in standard form. So if you have an x to the fourth, an x to the third, an x squared, the one that's in front of the x to the fourth, because standard form you have to write it that way, is the leading coefficient. So your leading coefficient is this a, okay? And why can't he be 0? He can't be 0 because what's anything times 0? It'd be 0, right? So if you made that a 0, that would mean there is no 0 anymore, or no x squared anymore, excuse me. And when there's no x squared, you can't have, it wouldn't be a quadratic anymore. So you need an x squared in the equation. A 0 would mean there's none of them, right? And that can't happen. So your leading coefficient has to be there. You have to have an x squared in order for this to be quadratic. And so let's take a peek at some other equations and decide, how do you know if it's quadratic or not? Okay, see this x squared? And you see how that's the highest power and their x squared is there? This is quadratic. Okay? This one, do you see how it has an x squared but also has a higher exponent of x to the third? This is not quadratic. And let's talk about, what do quadratics look like anyways? They're either parabolas that are smiling or parabolas that are frowning. And we'll talk about how you know when it's going to smile or frown. But that's what parabolas or quadratics look like. Okay? If we graph this, it would not look like that. So because of this, okay, this is not quadratic. Okay? This one, it has the x squared, and it doesn't have an x third, x fourth, nothing higher than that. However, this root x is weird. And so this is not quadratic because of this. Okay? This one, it is quadratic, it's just not written in standard form, right? So do you see how it has an x squared? Okay? So if we wanted to write it in standard form, see how it's a negative x squared and a positive 10, right? This is quadratic as well. It just wasn't written in standard form off the get-go. So what does it mean to be quadratic? To be quadratic, you have to have an x squared and no x third, x fourth, x fifth, all the way up to whatever, and no square roots. Okay? Okay. All right, so let's continue. Let's talk more about quadratics. Okay, so here's one of the things I want you guys to be able to do by now. You need to be able to write things in standard form, right? We did this with polynomial unit last unit. The only difference is we have an equation now, and that's okay. So what we have here is we have this equation, this quadratic equation. How do I know it's quadratic? Because you have an x squared and nothing higher than that. Does that make sense? It has an x squared and nothing higher. And so what we're going to do is rearrange this so that it's written in standard form. And then we're going to state what the leading coefficient is. So we're just working with vocab here. Okay, so to write it in standard form, we're going to want this piece to be written first, which would be negative 2x squared. Then we want the plus 4x. Then we want the plus 10. So this is standard form quadratic. Okay, so there's something. So you, right there, you know how to now put something in standard form quadratic. And now what's the leading coefficient? Your leading coefficient is the number right in front, your a value. Okay, it's your a value. And it's a negative 2. Okay, the reason we're talking about that is because it's going to take us to the next step here in a minute. Okay, and why did I call it the a value? Because remember, the standard form of a quadratic is y equals ax squared plus bx plus c. Your a value is your leading coefficient. Okay, all right, how do we get this one in standard form? Well, we need to get all of these pieces all together on one side, okay, and then we'll talk about what is over here. Okay, so we need to subtract the 6x over. And we need to subtract that 5 over there as well. Now there's nothing over here. So what's nothing? If there's nothing over there anymore, something has to be there. It'd be a 0, right? So 0 equals, and we have 4x squared minus 6x minus 5. So there's our standard form. Now what does 0 actually represent? When you are dealing with a quadratic, 0 is also known as y. So you could also write it as y equals 4x squared minus 6x minus 5. And we'll see more of that later as well. Okay? So now we have it in standard form. We have all the pieces together, written in standard form. Okay? And what's your leading coefficient? 4. Okay. All right. So now what else do we need to do to kind of think about what quadratics look like? We also need to know how to evaluate them. And so what we're going to do is it says if we have the function 2x squared minus 3x plus 1, what is the value of negative 2? What point must lie on the quadratic graph based on this calculation? So first, let's plug in a negative 2. So do you notice how they said f of negative 2? And that negative 2 is in parentheses like the x was. We're taking x out, putting negative 2 in. So f of negative 2, we're going to take x out. see, and put -2 in, and notice I'm using parentheses. Okay, and now we're going to go and evaluate this in our calculator. Okay, we clear this out. Apologize for the glare. That's a little bit better. So we're going to do 2 times -2 squared. Oops. Parentheses first, Miss Martin. Delete. Squared. There we go. So 2 times -2 squared minus 3 times -2 plus 1. And we get 49. And did I put a minus sign there? I'm going to check something real quick. For some reason, I'm thinking I didn't do a minus sign and I did a negative. Oh, yeah, I did. I could tell because of the size. It's not 49, it's 15. My bad. When you're using these calculators, do you see how sometimes you have to be careful because the minus and negative sign, and I went a little too fast. But you see how this one, the negative, I wanted it to be -3 times -2, but I accidentally typed the negative there. And I could tell because they were the same size. The minus sign is much bigger, and it's right in the middle of your setup, where the negative sign is a little bit higher up. Okay, so just be careful with the negatives and positives, and there's an example why. That's a big difference, right? Now, I'm also going to show you how to check this. This is an equation. When you have your x's, you can go to your y equals and graph it. So let's graph 2x squared minus 3x plus 1. I went to my y equals, right? And you can graph it, but we just need to go to the table. So second graph takes us to the table, and they want to know if our x is -2, what is our y value? And it's 15. So what does this mean? What point is on this graph? When you plugged in a -2 to this equation specifically, you got out a 15. What that means is when your x is -2, your y is 15. And so that point, -2, 15, is on this graph. And if we look at it, if I hit the graph button, you can see that -2, 15. I'm zoomed out a little bit. I apologize. Let me zoom, standard. And if we look at -2, we can see it at 15. My problem is you won't be able to see it because it's a little bit higher up since my graph's only going 10 by 10. Okay? All right. So what else do we need to know? Okay, let's talk about the a value. I'm going to put it nice and big on my notes so that when I'm looking back on it, when I'm doing my homework, I can find it. Okay? Let's explore the quadratic equation a bit further. A represents the leading coefficient, right? What does A do graphically? What does the A mean? Okay? Do you remember when we used to talk about lines and we talked about y equals mx plus b? The m is the slope, the b is the y-intercept. For exponential functions, the a was the y-intercept, the b is your growth or rate of decay. So now what we're talking about is, okay, so for quadratics, what do these letters mean? What do they represent on the graph? Okay, the a value is super powerful. The a value is going to tell you, are you ready? I'm going to give you a little prelude. The a value is going to tell you if it's smiling, meaning like this is called concave up, a concave up, because it's going up with the arrows, a concave up parabola. Okay, don't forget the word parabola, that's what the shape is called. And the a value will tell you if it's smiling because the leading coefficient, will be positive. When your a value is negative, your parabola is going to be concave down or frowning, okay? The a value also tells us the shape of the parabola, whether or not it's going to be wide or narrow, okay? And so let's examine it and figure out a way to help us identify what the a value is doing. We're always going to use y equals x squared, which is a standard, it's called a parent function. It's the most standard generic equation for a parabola, okay? So we're always going to utilize and compare to this. This is called the parent function, okay? All right, so let's go into our graph paper and let's sketch it. So the first thing is, what does x squared even look like? Because we might as well go graph it and then sketch it real quick on all of these graphs. So y equals, and then x squared. And let's graph it and see what it looks like. And if your calculator isn't in the standard 10 by 10 range, hit zoom 6, and that will put it in the standard form. Okay, so you'll notice the parabola starts at 0, 0. That's where your turning point is. Okay, and then it goes to 1, 1, and negative 1, negative 1. Okay, so it's pretty symmetrical. All parabolas are, and then it keeps going up, and by the time you're at 4, you're at 10. Okay, so let's just sketch this. Okay, I'm going to sketch it on all of them because for all of these, we're always going to compare it to this x squared. And I'm going to label it so I know. Okay, so what I'm doing is, because I'm taking this generic y equals x squared, I'm going to change the a value. Notice the a value is 1 for all of these, right? If I were to make the a value a negative 2, what's it going to do to my graph? If I make this a value a 1/2, what's it doing to my graph? If I make the a value a 4, what's it doing to my graph? So if I manipulate this equation and change the a value to negative 2, what's happening? Okay, so let's go to our y equals. Okay, I'm going to leave the x squared there so I can compare it. So in blue on my calculator, it's going to graph x squared, and in red, it's going to graph negative 2x squared. So negative 2x squared. And let's graph them. Okay. So what do you notice about this graph compared to this one? So this is your parent function. This is what a standard parabola is going to look like. And when I change its a value to a negative 2, it is now concave down. Okay? And it looks a little narrower. I don't know if you can tell. If you probably definitely tell if you're on your own calculator. It looks a little narrower, like it's more, right, pushed in, and the x squared is a little bit bigger. So we'll just talk about that negative 2. Okay? Let me grab a different color here. So here's what the negative 2x squared. Oh, good choice. That one doesn't work. Okay, so what is it going on here? So y equals x squared, okay? A 1 is positive, right? So that one was smiling, but once I changed it to a negative 2, because of the negative, it made it concave down. So a positive a will be concave up, and if you have a negative leading coefficient or a negative a value, it's going to be concave down. Okay? And that's a lot, right? So if I quickly said y equals negative 3x squared, you're like, oh, I know that it's going to look like this. Okay, so it tells you about the shape. All right, what if I compare, right, there's a 1 there, so think about that. There's a 1 there. What if I change the a value from a 1 to 1/2? What do you think it's going to do to this graph? Is it going to make it concave down? Is it going to make it wider, narrower? What do you think the 1/2 is going to do? So let's go find out. I'm going to leave the x squared there again so I can compare them. And this time I'm going to graph 1/2 x squared. Okay, you ready? So here's my x squared, right? My first graph. And I made it 1/2, and there's what the 1/2 looks like. Okay, has the same turning point, but it's wider. Interesting. Okay, so when your a value was a 1, right, here's what it looked like. It was concave up, and when you changed it to a 1/2, it got wider. And so let's compare 1 to 1/2. Which number is smaller? 1/2, right? So the smaller the a value, the wider it is. And here's why. Because your slope, instead of going up 1 over 1 on average, okay, these are just rate of changes. They're not slopes because it's not linear. So it's going about up 1 over 1 for the first little bit, where 1 over 2, if you go up 1 over 2, it's a further stretch, okay? So a 1/2 is going to make it wider. Now, you don't technically have to ever memorize this because you always have your graphing calculator to test it. So if I said, hey, what's wider, y equals 2x or y equals 1/2 x, go graph it. Okay, now let's compare this one. So if changing it to a 1/2 made it wider, what happens if I change it to a 4? Well, let's see. 4x squared. All right, there's my original graph. A is 1. And when I change that a value to a 4, woo, steeper. Because it's going up 4 over 1. So it's going, that vertical change is much bigger. Okay, so this is the 4x squared. Okay. The big number makes it steeper. So in other words, more narrow instead of wider, right? Okay, so I have a challenge for you. Let's think about this for a minute. If I have, I think I have blank paper on the back of this side. Yes, I do. Okay, so if I have y equals x squared, if I have y equals 1/4 x squared, if I have y equals 5x squared, okay, let's think about how these would look, okay? So y equals x squared, okay, just sketch it, right? Just make up a parabola, okay? Here's x squared. What's the 1/4 going to look like? Okay, remember it's going up 1 over 4, so it's wider. Okay, and then the 5x squared, that big number, is going to make it go up 5 over 1, so it's going to be going up faster, so it's going to be narrower. Okay, so when you're working your way from the middle to the outside, it goes from big to small when you think about it being all put together in one picture. Okay? Now, what if you throw negatives in there? The negative does the same thing. Okay? So if you have a y equals a negative x squared, a y equals a negative 1/4 x squared, and a y equals a negative 5x squared, it's still going to work the same way, except for it's going to be facing down. So here's, say this is your negative x squared graph. Okay? Your 5 is going down 5 over 1, so it's much steeper. So it's still going to be the narrow one. It's just facing downwards instead of upwards. So it's almost like if you want these to be negative, just turn them this way, right? Okay, and the 1/4 is still wider. Okay, the negative just means it's going down instead of up. So it doesn't change. So it's still, if the big number is if the big A value is still going to be thinner. Does that make sense? Okay. All right, so let's get a little bit more practice here. So let's fill out this summary section. So let's see. So the graphs of quadratic functions is different than linear and exponential functions because it has a vertex, also known as a turning point. And we're going to talk about that here in a minute. Okay, but right now we're talking about the A value. Okay. So the parabola will open upwards. Oh, my image got lost. Go ahead and just draw this in for me if you don't mind. The parabola will open upwards, okay, when A is what? So we're talking about this A value, okay? It's going to open when A is positive. When A is positive, by the way, if your graph looks like this, what do you notice about your turning point? It's a minimum because it's the lowest it ever gets because a upwards parabola is just going to keep going up forever. The parabola will open downwards, in other words, be concave down, okay, if A is negative. And this one will have a maximum, and we'll see that here in a minute as well. So the A value is going to tell us if it's smiling or frowning. And the A value also tells us if it's narrow or wide, okay? The parabola will be wide, okay, wider than this function if, so what makes it wide? When the number is smaller than 1, right? In other words, don't say smaller than 1 because I don't mean negative. Like you can't, when you're smaller than 1, do you agree? -1, smaller 1, -2? That's not what I mean. It has to be between 0 and 1. It has to be a value that's between 0 and 1. So example, 1/2, 1/4, 2/3, etc. Okay, and the parabola will be thinner, and I like the word narrow or steeper, when the number is greater than 1. Okay. Sort of like what we talked about with exponential functions, right? When we talked about what's it going to do when it's between 0 and 1 and what's it going to do when it's greater than 1. If it's greater than 1, it's going to go up a heck of a lot faster, so it's technically a thinner parabola. Okay? And there's a little sketch of what happens when you change it to something, right? Okay. Last piece. So let's graph one and really talk about the pieces all together. So consider the quadratic y equals x squared minus 2x minus 8. Now on delta, what you're going to have to do is plot 5 points when you're graphing a parabola. Okay? Of those 5 points, you need to plot the vertex. Okay, we'll talk about that, which is also known as the turning point. And you also need to plot the zeros. The zeros are also known as the x-intercepts or the roots. Okay? And then we can plot some other ones as well. And I'm going to talk about one in particular that comes back up in this equation, ax squared plus bx plus c. Okay? So using your calculator, let's generate a table and graph this parabola. So let's go ahead and go to our y equals. I'm going to clear out my old equations here just by hitting the clear button. And let's go graph x squared minus 2x minus 8. X squared minus 2x, this time is smart, not negative, minus 2x minus 8. Okay. And I like to look at the graph first to get a general idea of what it's going to look like, because see how this is 10 by 10? So is my graph. So it will look like this. And you can see where it turns. It turns somewhere over in here. Okay. I can see where it crosses the x-axis. So I can already tell that at -2 and at 1, 2, 3, and at 4, those are 2 points that will be really good to graph. So let's go plot those right now. At -2 and at 4. Okay, those are known as the zeros. Okay. All right, and then the turning point, can I really tell? I kind of can, but I'm going to use my table to help me graph some more points. Oh, another point, let's look up here again, is you can tell where it crosses the y-axis. You see, so here's your zeros. Those are your x-intercepts. It crosses the x-axis at 2 places. And here's your y-intercept, and it's down at -8. Do you see our equation up here? Do you see a -8 somewhere? Yeah. So this -8 in your equation, so let's think back to ax squared plus bx plus c. The c value is your y-intercept. Just like when we talked about y equals mx plus b, the b was your y-intercept. So the number that's by itself with no variable is always your y-intercept. Isn't that cool? Okay. All right, so let's see. -8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So that'll be a good point. We'll see that on the table here. So let's go to our table. All right, and let's plot some nice points. These are too big because you can't plot that high. So what about -3, 7, -2, 0, -1, -5, 0, -8. I'm going to make my table bigger. 1, -9. 2, -8, 3, -5, 4, 0. Okay. The reason I want to make my table bigger, and I'll probably do this for my notes next year, is because I want you guys to see a pattern. What do parabolas do? Parabolas start, they go down, and then they come back up, and this is called symmetry. So something that's over on this side has a point exactly where it is, but over on this side. Okay? So you're going to notice symmetry in your table. So what do you notice? Right? On my graph, when you look at it, you see 7, 7, 0, 0, -5, -5, -8, -8. And then this number all by itself in the middle, and that's your turning point. Okay? So you see the symmetry? 0, 0, -5, -5, -8, -8, 1, -9. So this guy right here, who's all by himself in the middle of that symmetry, is your turning point, which is also known as a vertex. Okay? And then do you see those zeros? You see those zeros, right? That -2 and 4, that's those two places. Those are your zeros. It's where your y is 0. So this is one of your zeros. 0 number 1. And then there's 0 number 2. So on delta, they're going to make you graph those 3 points, and then it's up to you what other 2 points you want to graph. Anything you want on delta, you just plot those points and it'll draw the parabola for you. Okay, so we've got the y-intercept as well, which is important, right? Here's your y-intercept. Okay, so there's some labeling some points here. And so let's just plot some more. So -3, 7, I'm going to graph the whole thing because it really helps you kind of get a better idea of how it looks. So -3, 1, 2, 3, 4, 5, 6, 7, -2, 0, -1, -1, 2, 3, 4, 5, 0, -8, 1, -9, 2, -8, and watch, I'm going to graph this really quickly now because it's symmetric. See that symmetry? So go over 1, and it's going to be symmetric to that point. Go over 1, symmetric, over 1, symmetric. So this symmetry means that if you were to fold it, it would land on top of the other half, okay? And so let's draw it the best you can. Don't make like it connect the dots. It's very U-shaped, so be very casual and make it U-shaped, and don't make it rugged and make it look like the letter V. It needs to look very U and parabola-like. Just do the best you can. That's why it's important to have those points. Okay? So there's your vertex and turning point. Turning point, okay? Here's your zeros, like I labeled before. Here's your y-intercept. And like I said, on delta, you have to do the vertex and 2 zeros and then any other 2 points you want, and it'll create the shape for you. Okay? So what did the a value tell you about the shape of the graph? So let's go back up to our equation. Do you remember how it was a positive 1x squared? That meant that the shape of the graph was going to be smiling, right? Concave up. Minus 2x minus 8. Okay. So the c value is your y-intercept. And the a value is positive, so it's concave up. Okay. All right. So state the coordinates of the parabola's turning point. This is also known as the vertex. And please notice, not only is it the vertex, but it's the lowest this graph ever gets, which is called a minimum, right? So where did that happen? That happened at 1, -9. The middle of the pattern, right? The middle of the symmetry. Draw the axis of symmetry of the parabola and write its equation below. So where does the symmetry happen? It happens at the turning point. Okay. And so right here, I'm going to use blue here, is where if you folded it, if you fold the graph right here, okay, this is called the axis of symmetry. It's a line where if you were to fold this paper, these points are going to lie on the other side perfectly and match up. Okay, so that's called an axis of symmetry. And where did it happen? It happened at the point 1, -9, right? And then what kind of a line do you notice? This is vertical, right? A vertical line goes through the x-axis, and where did it go through the x-axis? At 1. So the equation of this line is x = 1. In other words, where this happened. So that's your equation for your axes of symmetry. We'll get more practice with that too. It's not a huge skill in algebra, but it's there. What are the x-intercepts of this function? Remember, the x-intercepts are also known as the zeros or roots. Okay. they happened at -2 and at 4, right? Another thing you can say is they happened at 2 and 4, right? With the brackets, because you're listing them, the braces. Okay, so there's some vocab. And then let's talk about this one. This is also on your delta assignment. So the quadratic function f of x has selected values shown in the table below. What are the coordinates of the turning point? I'm not giving you a graph, I'm just giving you a table. So, no equation, you can't use your calculator here. Oh no, so what are we gonna do? All right, so how do we know the turning point? The turning point is gonna be the number in the middle of your symmetry. So do you see this 4 and 4, 9 and 9, 12 and 12, and there's your turning point. It's also known as your vertex. Okay, so turning point, I abbreviated TP. And where does it happen? It happens at 2, 13. Is the turning point a maximum or a minimum? Well, that'll be easy to tell. A maximum means it's going to be the biggest number on that table. A minimum means it'll be the smallest number. See how the numbers are getting bigger, 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 and then smaller, smaller, smaller? So this is the biggest that number ever gets, right? It's the biggest, so that would be a maximum. Because all the other numbers around it are getting smaller, okay? Would this parabola be concave up or concave down? Well, let's think about this. If it has a maximum, okay, let me draw 2 sketches because there's only 2 choices, right? Your parabola is either going to look like this or it's going to look like this, okay? Which of these graphs has a turning point that's a maximum? Well, this one, that's as low as it gets, it turns back up, so that one has a minimum, and this one has a maximum. So it's this type of graph that we are seeing in this table because it has a maximum. So a maximum is going to be concave down. So for this equation, ax squared plus bx plus c, we don't know the equation. We're not writing it. But what do we know about it? What do we know about the a value given this information? Well, because it's concave down, right? Because it's concave down, the a value is going to be positive or negative? It's going to be negative, right? Good. And that's it. So that's what the vocab is on today. Just understanding, graphing these parabolas. You're going to get great practice in developing those skills in Delta. Please don't skip this homework. Don't skip this lesson. This is going to really help build that foundation, and it'll make this unit so much nicer for you. And this unit is not bad, but you've got to put in that time and effort. Okay? All right, you guys. Let me know if you have any questions or concerns. And other than that, just do your best to get this assignment done. Okay?